Hello and welcome to lesson 84, my DP chemistry curriculum. Today we're going over reactivity 2.2.7 and 2.2.8. For the first section, we're going to be talking about how energy profiles can be used to show the activation energy and transition state of rate determining step and multi-step reactions. We'll be able to construct and interpret energy profiles from kinetic data. In the second section, 2.2.8, we'll talk about the molecularity of an elementary step as the number of reacting particles taking part in that step. We'll be able to use the term unimolecular, bimolecular, and termolecular. So with that said, let's go right into it. So in the previous section, we talked about multi-step reactions, multi-step reactions, and how they can be demonstrated in multiple ways, but they can also be demonstrated with energy profiles. Demonstrated, whoops, created with energy profiles. And it's kind of the easiest way to look at them because we get a lot of information from that energy profile. So let's take an example of some multi-step reaction. If we have A2 plus 2BC reacts to form B2 plus 2AC. Now, we can say there are two steps in this, so we'll just assume a step one, and that step one might be A2 plus BC reacts to make AB plus AC. Then we'll say step two, we'll go ahead and take that AB and BC, AB from the previous step as a product plus BC as a reactant from the previous step, and we can react these to make our B2 plus 2AC. So here's our step one and step two, and we'll represent both of these reactions in our energy profile now. So as we make our energy profile, we're going to take care to represent each step properly. We'll make sure that our y-axis is energy, whoops, energy, as this is an energy profile, and our x-axis will determine as reaction progress, so we can determine the progress of the reaction. Now, in this process, we'll say this is, for instance, why don't we say the whole thing? We'll give it a delta H of negative, or I guess I should say delta H is less than zero. So we'll say that this is exothermic. So we'll do our step one, step two, and then we'll end down here. So in this first step, we have our A2 plus BC as our reactants, and we have our intermediary steps. We'll get to that in just a minute. This is our step one. In our step one, we're going to have a couple points here. We have our activation energy for step one, EA1. And then as this reaction progresses, we get to our products of step one. If you remember from our previous one, this is our intermediary, not our transition state. So our intermediary in this case, our intermediate is going to be RAB. It is neither in the reactants or products, but it is in the intermediate phase. So we're going to put our AB right here. In this, from AB reacting with our remaining BC, we now have our second activation energy. This is EA2. This represents our step two. Finally, we have our final products down here, B2 plus 2AC. So this is our reaction energy profile, and we can determine quite a few things from it. In this energy profile, the first thing we can determine is that two peaks. That tells us there are two steps, as each step will have its own activation energy and therefore a peak. Our dip represents our intermediate. We see that our activation energy 1 is greater than activation energy 2. Therefore, we can determine step 1 is rate determining. Usually the higher activation energy is the rate determining step. Lastly, if we see our delta H is less than zero, which it is in this case, we know that this is exothermic. So we can determine quite a bit just from an energy profile of a reaction. We can look at even larger multiple reactions with different activation energies. So let's go ahead and see what that might mean. So for instance, if there are multiple activation energies for each step, we know that the largest activation energy, that being the change from previous reactant to peak, I'm going to put that in parentheses. That change is usually going to relate in our rate determining step. And it can get a little confusing sometimes. Um, and we are just looking from the beginning to that highest energy state. So if we have another reaction, and this time I'll make it a random three-step reaction. In this random three-step reaction, we have three activation energies here. One, two, three. EA1, EA2, and EA3. So a couple things we know about this is EA2 is going to be rate determining. But one of the other things we also get is that the EA overall is actually going to be the reactant to highest energy transition state. So in our case, our EA overall will be this whole bar matching with that peak. And so something to know about the activation energy of a reaction is it comes from the overall reactant to highest energy state, not just the largest activation energy of a given step. So that is our reaction profiles, as well as activation along with it. We're going to briefly now talk about molecularity. Molecularity is quite simply the number of species reacting in an elementary, elementary, I think there was an A there, elementary step. So we have the three different kinds. We have unimolecular, uni referencing one, so a molecularity of one. You generally see this in decomposition steps. So an example of this might be the decomposition of like ammonium nitrate or ammonium nitrite. And as this decomposes, maybe it turns into nitrogen, nitrogen gas plus water. That'll be 2H2. So it's a molecularity of one referencing our reactant. We could have a bimolecular reaction, which is going to be of two, a molecularity of two. An example might be the decomposition of two HI molecules. Now you'll notice this may be only one specific species or one specific molecule, but because there are two of them, It is therefore bimolecular. So that's sometimes a little confusing for students. Just because it is one species does not mean there aren't two species reacting. Or just because there's one molecule doesn't mean there aren't two reactants. It's just two of one, which is still a bimolecular reaction. We may also have termolecular. You will never have more than three in an elementary step. An example of this might be we take two nitrogen monoxides and we react them with oxygen to get two nitrogen dioxides. And this would be termolecular because you have two plus one for a total of three. That's one molecule, that's two molecules, and that's three molecules. So all you need to generally do with molecularity is just identify the molecularity of a reaction. You don't really have to do much with it. We'll come back to it when we're starting to talk about like SN1 and SN2 reactions, but that's way down the road. Anyways, I hope this helps and have a great day.